What does it mean for a function to be continuous? Welcome to this video where we explore that concept and look at it through the lens of sequence convergence. Let's start off by just talking about the intuition of continuity of a function. I think people's intuition is usually pretty good about functions and whether they're continuous or not. In fact, if we start off by just looking at these three functions that I've drawn, it's pretty obvious that this one is not continuous, this one is not continuous, and this one is continuous. And our intuition from our perhaps even high school days is that the idea of continuity is deeply rooted in this flow of the function, that you can draw the function without lifting up your pen. And anecdotally, that often does correctly correlate to the function being continuous. But what we want to do in this lesson is actually write and explore a formal definition of continuity that rigorously conveys this concept of a function being continuous versus not being continuous rigorously. If I asked you right now to define continuity rigorously, and the best you could come up with is this intuition of not lifting up your pen, that's not really good enough for being rigorous in your definition. So we're going to look at several definitions of continuity, and in this particular video, we're going to be looking at the sequence convergence definition of continuity. Okay, so the definition for continuity using sequence convergence is this. Let the domain be a subset of Rk. A function f that uses this domain is continuous at a point x star that is in the domain if for every sequence in xn that is also in that domain converges to x star, then the sequence of f of xn in the output of Rm converges to f of x star. F is discontinuous at x otherwise, and f as a function overall is continuous if it is continuous at all of the points x in the domain. So to break down this definition of sequence convergence, the idea is that when you plug a sequence xn into the function f of xn, we want those sequences to behave similarly in the function, and the similarity that we're looking at is their limit. So we want the limit of the sequence in the function to behave in the exact same way if the limit of that sequence outside of the function is the same. So all sequences that converge to a particular limit must be inside of the function converging to the same limit also. And the reason why this is pretty helpful is that we can actually use this definition to disprove continuity. So the tagline here is that every sequence that converges to x star, f of xn must converge to f of x star. And this is true for all relevant sequences in the domain. Notice that f of xn is actually generating a new sequence. Xn as a sequence is being transformed by the function into f of xn, and we want the new transformation of that sequence to be converging to f of x star. And this definition becomes really useful in disproving continuity because we can demonstrate a function is not continuous by providing a sequence that converges to x star in the domain, but then f of x star is not converging, so f of xn is not converging to f of x star inside of that function. Okay, let's take a look at an example of this. Yeah, so sorry, this just summarizes what we're saying. When you're disproving continuity, f is continuous at x if every sequence satisfies the convergence requirement. So to disprove continuity, we only need to provide one sequence that violates this convergence requirement, and then we're done. Okay, so the example that we're going to look at in this video is a simple function here. We'll look at two examples, but the first one we'll look at this is a simple function that is piecewise, and f is being mapped to 2x when x is less than 1, which is this one here. And then when x is greater or equal to 1, it's being mapped to 3x plus 1. So it has a steeper incline and a vertical axis intercept if it went that far of plus 1. So the question is if f is continuous. Obviously the answer is no, there's a huge gap in this function here. And what we want to do is use our sequence definition to actually prove that this function is discontinuous at x equal to 1. Okay, so the way that we want to do that is by using this definition here, by providing the existence of a sequence converging to 1, where f of that sequence is not converging to f of 1. And if we do that, we disqualify this definition and we disqualify the function as being continuous. Okay, so before we look at the answer, what's our goal here? We want to find a sequence that is converging in the function to 1, but then when you plug f of 1 into the function, it is jumping to this value of 4 here. So if we look at a sequence that is converging to 1 from the left, then the function as a graph here, you could see this line, and then the sequence plugged into the function will be along that line also. And this line is behaving in such a way that you would expect as x approaches 1 is that the line will converge to 2. But because the function actually is defined like this, it jumps up when x is 1 to 4. So we can use this to rigorously show that there's a discontinuity here. So the sequence that we can use is going to be xn is equal to 1 minus 1 on n. So that way 1 on n as n goes to infinity will go to 0, and so the limit is going to be 1. And then the minus 1 on n as opposed to plus 1 on n will be useful because it's approaching from the left, which means that when we plug it into the function, we're using this line here that goes towards the gap. So let's look at it written down. Consider the sequence xn equal to 1 minus 1 on n, which is always in the domain R. The limit of this sequence is equal to 1. And in some questions, you might, if this is an exam or assignment, this type of question, you might want to prove with your epsilon definition of sequence convergence that this is true. But for now, we'll just take that as being obvious. And so we have here our sequence converging to 1. And if we consider the transformation of the sequence in the function, f of 1 minus 1 on n will just be equal to 2 times 1 minus 1 on n. And we know this because 1 minus 1 on n as an input is always strictly less than 1. So we get this new sequence here. And that sequence, of course, will converge to 2. And again, depending on the question context, you might want to prove that rigorously. And this is going to be the foundation of our problem, which is that f of 1 is 4, but then f of the sequence converges to 2, not 4. So together we have a sequence converging to 1, but f of the sequence not converging to f of 1. And thus we've proven that f is not continuous at 1, and therefore f is not continuous as a function overall. Pretty straightforward. Let's take a look at another example now that is a bit harder. For this example here, if we have 2 dimensions of input, x1 and x2, and we define our function like this, f of x1 x2 is equal to x1 times x2 divided by x1 squared plus x2 squared. This is not defined when x1 and x2 is 0, 0, because then you're dividing by 0. And therefore, to define the function for all inputs, we can just manually define the function as equal to a when x1 and x2 is 0, 0. And what we want to do is prove that regardless of what a is and how you choose a, it's impossible to have f be a continuous function. So with any choice of a that you would like, you cannot make f continuous. And we want to prove that. So how can we do that? Well, it's a bit different to before because we can't just simply demonstrate one sequence that is converging to a particular value and then f of that sequence converging to another value that's not part of the function, because here you can choose a to be whatever you want. So if you just look at one sequence that converges appropriately, then if you chose a to be equal to f of that sequence and then that's the limit, then it will at first glance not violate the definition. So instead, what our approach is going to be is like this. Here, we're going to find two sequences that converge to 0, 0, but then f of these sequences are going to converge to different things, and therefore it's impossible for both of these to be converging to f of 0, 0. F of 0, 0 is a, and we can't choose a to be the top number because then the bottom one doesn't converge to it. And we can't choose a to be the bottom number because then the top one doesn't converge to it. And together that implies that it's impossible for every convergent sequence that goes to 0, 0 to have f of that sequence converging to the function value. Okay, so to look at the solution for this, we can look at two sequences, one on n, 0, and one on n, 1 on n. If you're wondering how to choose the sequences, take a look at the function here. The idea is that when we plug in our sequence, we want to get some sort of cancellation or multiplication that changes the narrative of how it will converge. And if we plug in 0 and 1 and n together, the numerator will become 0 and the denominator will not be 0. So you will get this just being a value of 0 and therefore converging to 0. And then if you plug in 1 and n and 1 and n, then you will be able to get s1 on n squared on the top, 1 on n squared plus itself on the bottom, and then that will just be equal to a specific number. And then we've got it converging to 0, converging to a specific number, and that's 1/2, and therefore show that those two numbers aren't the same. So look at it written down. As xn is equal to this and zn is equal to this, notice that both of these are converging to 0, 0 because every individual component of the sequence converges to 0, 0. Now, theorem is that if the component of a sequence if the component of a vector converges to something and every component converges, then the whole thing converges. So, yep, we got both of those sequences going to 0, 0. And then when we plug those sequences into the function, we get f of xn being equal to 0. So therefore the sequence converges to 0. That's pretty obvious because the sequence is just 0, 0, 0, 0, 0, 0, 0, which converges to 0. And then likewise, when we plug in now f of zn, we get some cancellation that is nice, where it's equal to 1/2. And so that will converge to 1/2 because the sequence is just 1/2, 1/2, 1/2, 1/2. As these are not the same thing, it doesn't matter what a we choose because they should both be converging to a, and a can only be 0 or half, not both of them at the same time. So therefore, as both xn and zn converge to 0, 0, but f of xn and f of zn converge to different values, regardless of the a that you choose that's a real number, f cannot be continuous. Okay, so that concludes this video, which is looking at the continuity of a function using our sequence definition.